Okay, part 2. This is a 22 kilogram crate slides down a ramp that's inclined at 29 degrees into horizontal to the horizontal, 29 degrees to the horizontal, onto a spring. Of course, force constant 890. The spring compresses a distance of 0.3. Before the crate stops, determine the total distance that the crate slid across the ramp, including the spring compression. So, coefficient of friction between the ramp and the crate is 0.2. Alright, so if you're drawing this situation, you've got essentially a box that slides down a ramp a particular distance h, and it compresses a spring and then comes to a complete stop. Now this distance here is delta d, how far it slides down the ramp until it hits the spring, plus 30 no, including the spring compression, yes. So we don't need to really, no, we won't need to consider that. So I do know that this is just delta D. I know that this is 29. So I know that since this is delta D from here, essentially from here to here, the, oh, you can't see that so much. From here to here, the relationship between the distance that it slides down and the height that it slides down is the, since this is opposite and opposite and hypotenuse, the sine of 29 is equal to h over delta d. This is going to be a handy formula a little later on. Okay, and now I know that under initial conditions, it had no kinetic energy. All it had was gravitational energy. Then it slides down the ramp and it experiences friction. So initial conditions are only gravitational. Slides down the ramp and it experiences thermal energy through loss through friction. And in the end, all this gravitational energy gets turned into thermal energy, and then anything that's left over is used to compress the spring, so elastic energy. Alright, and so if I figure out this, the height of this object is h, its mass and gravitational energy is mgh. That's the formula for gravitational energy. Thermal energy is force of kinetic friction times UK, and then the elastic energy is 1/2 kx squared, and I know that x is 0.3. And if you notice, the thing that I'm looking for, delta D, hasn't even shown up yet in my equation, but if you look back over here, delta D is see, did I do that right? Opposite over hypotenuse. Yep, that looks pretty good. If I try and solve for h in this situation, it's delta D sine of 29 is equal to h. Now you have to solve for h because now you can get rid of this h over here and put this in its place, because h is equal to that, and so I'll do that. Now the force of kinetic friction, you know what, I keep writing this equation wrong. Let me go back. Thermal energy is not Fk UK, my mistake, it is Fk delta D. Okay, so that is actually, this is the distance that it slides times the force of kinetic friction is how much thermal energy it loses. So there's our delta D, and here's our delta D as well. And so we know that H is delta D sine of 29, then times mg equals Fk delta D plus 1/2 kx squared. Fk is actually Fnuk, but I need to figure out the normal force on the box. So if I go back and think of the box here, remember the normal force is equal to Fn. In this case, it is equal to Fgy. The normal force is equal to Fgy. But in this case, since this is 29, that little thing right there is 29, then the normal force is equal to that. And then so since this is Fg, then this is from a couple of chapters ago, the normal force is equal to the force of gravity times the cosine of 29. So if you look at this, this is the adjacent side to 29, and I'm trying to figure that out. This is times uk. And so the force of kinetic friction, back over here, Fn is Fg cosine 29, uk is uk, so Fk is equal to this. Alright, due to this picture here. So Fk is here, which is force of gravity is mass times gravity, times the cosine of 29, times uk, which I'm going to write the uk in the front, just to alleviate any plus 1/2. Oh, and then also times delta D is in here as well, which I'll write in the front as well. So there's a lot of stuff in here, in this term. This mg cosine 29 is the force of gravity, which comes in from the normal force. The uk comes in because of it's the normal force times uk. The delta D comes in because all of this is friction, and then all of this is thermal energy. So this whole thing is thermal energy. This is normal force, and this is friction. Okay? And so you can kind of imagine how that got built. And then over here is still delta D times mg sine of 29. And so this is now where we're at here. Okay, and so let's go with trying to solve for delta D. To solve for delta D, I'll take this whole term and subtract it over. And so it's delta D mg sine 29 minus delta D u k mg cosine of 29 plus 1/2, equals 1/2 kx squared. Now I notice that I have a delta D here, and I can factor it out. mg sine 29 minus uk mg cosine 29 equals 1/2 kx squared. So delta D is equal to 1/2 kx squared divided by all of this, mg sine 29 minus uk mg cosine 29. now we have a water pump that is rated at 2 kilowatts, and it can raise, so that is 2,000 watts. It looks like the power. It can raise 55 liters of water per minute. Time is 60 seconds. It can raise 55 liters of water. That is, looks like it's going to raise 55 kilograms of water. At a constant speed from the lake to the top of the storage tank. How high is the storage tank above the lake? Assume that all the energy from the pump goes to raising the height of the water. Okay, and so it looks like the power of this pump is equal to the energy time over time. Well, what type of energy is this pump doing? It's making gravitational energy. Essentially, it's giving the water gravitational energy, and assume that all of the energy goes towards raising, and so this is an energy of gravitation. All right, and so the power is equal to mgh over time. And so I know how high, or that's what I'm looking for, how high it goes. And so if I multiply it by time, mgh, if I divide by mg, I get T times power divided by mg is equal to h. And that's how high it goes. It says the average human uses energy at an average rate of about 2 kilowatts per day. Again, 2,000 watts per day. This figure includes energy that is used outside the home, but not used to manufacture products. Well, that's not so important, really. Assume that on a bright sunny day, the solar energy striking the surface of provides a power of 700 watts per square meter. Solar energy striking a horizontal surface. You can get 700 watts of power from the energy. If a solar collector can capture 20% of that energy, and so you've got 700 watts per square meter, and a solar collector can capture 20% of that energy. And so how many basically of this 700, only 20% of it is useful. Okay, and I think I've got a calculator around here just to get these numbers. So 700 times 0.2. I guess I should have known that. Here, 140 watts per square meter is how much we can get for a solar thing per day. Okay. So, because on a sunny day you can get 700 watts per square meter. And so you can only get that much. Now, this is how much we need. This is how much we can get. But then also, we have 5 people, too. So we actually need 10,000 watts per day. And if one of these can only give us 140 watts per day, well, then basically we're going to have to take 10,000 divided by 140 to get groups, which is 71 of these square meters. Okay, this is per 1 square meter over here. This one was a little tricky, but you kind of have to imagine it as rates and sort of break it into groups. And so going back, we need 2,000 watts per day per person. For 5 people, that's 10,000 watts. Each day, the sun gives 700 per square meter, but we can only capture 20% of that, so for 140 per square meter. And so if each square meter has 140, then essentially if we've got 140 and we have 71 of them, 140 times 71, that should give us our needed 10,000. Okay? And that's basically the concept behind there. It says a discus traveling at 20 meters per second has 330 joules of kinetic energy. Find the mass of the discus. Energy kinetic is equal to 1/2 mass v mv squared. And so we know that it has 330 joules and it's traveling at 20 meters per second. And so in the end, the mass is 330 times 2 divided by 20 squared. Let's do the algebra on that. This is a chairlift takes skiers to the top of a mountain that is 320 meters high. The average mass of a skier, complete with equipment, is 885. The chairlift can deliver 3 skiers to the top every 35 seconds. Okay, determine the power rating. So the power rating is energy times, and this is gravitational energy again, times time, or divided by time. So in this case, we know that they're they're going a height of 320. This is mgh, by the way. And the mass of the skiers is 85, but there's 3 of them. And so we've got 385 times 9.8 times 320. And this is divided by 35 seconds. And that's the energy rating of, or sorry, the power rating of the thing there. If 25% of the motor's energy is lost to friction, what power must the lift be able to deliver? Okay, so let's say that this is the power that it needs, power needed. Okay, and so we know that we can get that number. I'm gonna call it Pn. This is the power that it needs to get those skiers up there. Okay, but we know we need to make more power, and so basically, if we have some sort of power, which I'll call power 2, and it loses 25% of this minus 0.25 of this power, and it should be, the leftover power should be the power that we need. If I take my power that I can produce, which I don't know, this is actually what I'm looking for, and I take away 25% of it, then I'm left with hopefully the power that I need to make the guys go up the hill. Okay, and so you basically solve for power 2 in this equation. So this is power 2 minus 0.25 power 2 is 0.75 power 2. And so to solve for power 2 is Pn divided by 0.75, whereas Pn is the power we need to get up the hill. Okay.